Hello students, let's start the first section of optics, that is nothing but interference. The preliminary knowledge of interference you can get with the help of this YouTube link. Here in this section we are going to see one case of interference, and that is through Newton's ring experiment. Newton's ring in reflected light is the first point that we are going to see over here. Next to that, we have to understand what are the applications of this interference or Newton's ring experiment. So some applications are listed over here that are nothing but determination of thickness of wire or determination of refractive index, then wavelength of incident light, radius of curvature of lens, testing of surface flatness and anti-reflecting films. So all these points we are going to see along with Newton's ring experiment. So what are the learning objectives of this particular topic? At the end of this video, you will able to arrange components of Newton's ring experiment to see the interference pattern. Then you can determine radii of bright and dark ring in Newton's ring pattern. You can determine wavelength of light using Newton's ring experiment. You can determine refractive index of liquid using Newton's ring experiment. So this is related to learning objective. Now let's talk about Newton's ring in reflected light. This particular experiment was performed and observed by Sir Isaac Newton, and basically here we are going to get interference pattern due to reflected light waves. That's why this particular experiment is having the nomenclature as Newton's ring in reflected light. So first we will see the construction of the Newton's ring experiment, then we will observe how is the interference pattern, and at last we are going to determine some parameters related to that interference pattern. So first talk about construction of the Newton's ring experiment. Here there is one source of light. Preferably a sodium lamp is used in this experiment. Then there is a glass plate which is inclined at an angle of 45 degree is placed in front of the sodium vapor lamp. A glass plate is mounted at the lower surface. On that there is a one plano-convex lens. Plano-convex lens is a convex lens of which one portion is convex and one surface is plain glass plate. In between the plano-convex lens and glass plate, there is a formation of air film. A thin air film is get generated in between the plano-convex lens and the glass plate. Light radiations from the sodium vapor lamp strikes on the glass plate, and due to the particular angle that glass plate has made, they will get bent towards the plano-convex lens glass plate system. The interference pattern you will get on the glass plate which is below to the plano-convex lens, and whatever is the pattern that you can observe with the help of traveling microscope. So this is the construction of Newton's ring experiment. Sodium lamp, then glass plate arranged at 45 degree, a plano-convex lens, glass plate and a traveling microscope. So here is the construction of Newton's ring experiment. Now let's see what happens when a ray is interacted with plano-convex lens glass plate system and how we can get interference through this particular Newton's ring apparatus. So here is the glass plate on which a plano-convex lens is placed that we have seen in the Newton's ring arrangement. When a ray AB is incident on the system, it gets partially reflected at the bottom of the curved surface, the point B. From here we can observe the reflection, and this is nothing but a ray 1. And another part, that is ray 2, we can get from the transmitted ray, which is partially reflected from the top surface of the plain glass sheet. The rays 1 and ray 2 are derived from the same incident ray by division of amplitude and are thus coherent. Ray 1 undergoes no phase change, but ray 2 acquires a phase change of pi upon reflection, since it is reflected from air to glass boundary. Interference does not take place between the rays reflected from the surface of lens and glass plate owing to their thickness. So, by the combination of ray 1 and ray 2, we are going to get the interference pattern. And here is the result. You can observe circular fringes over here. Why these fringes are circular one? This is due to the variation of air film in between the plano convex lens and the glass plate. At the point of contact, the film thickness is very small, and as you move towards outer edges, it goes on increasing. Therefore, the locus of the points having the same thickness fall on a circle having its center at the point of contact. Thus, the thickness of the film is same at all points on any circle having 0 as the center, and therefore these fringes are circular one. Another important point related to this pattern is at the center there is a dark spot. Why we observe the dark spot at this point of contact? Again, we have seen at the point of contact the film thickness is very small, and if we compare it with the wavelength of the light, then we can have the relation where the thickness is very small as compared to the light, wavelength of the light, and therefore at the point of contact whatever light wave get incident, it just get reflected back, but while having the reflection its phase changes by an angle of pi. Therefore, at the point of contact, there will be a destructive interference. As we know, in case of destructive interference, there is minimization of light intensity. Minimization means darkness will be there, and that is the reason at this point of contact or at the center, we observe the dark spot. Next to that, these fringes are called as fringes of equal thickness. Why this is so? This is due to the occurrence of alternate maxima and minima. These maxima and minima are due to the variation of the thickness T of the film. Each maximum or minimum is nothing but a locus of constant film thickness. Hence, the fringes are called fringes of equal thickness. So, this is all about the pattern that we observe over here. Now, the important point that will be the aim of our further slides is to determine the diameter of rings. As we have seen, these fringes are circular one, means of course that circle will have certain amount of radius or certain amount of diameter. If we know the diameter of these rings, then we can calculate further parameters. So that's why we have to calculate diameter of these dark rings and diameter of bright rings as well. So let's see. Determination of diameter of bright and dark rings. You might have seen the condition for constructive and destructive interference that are given as 2 mu t cos r is equal to 2m plus 1 lambda by 2 for constructive interference. That is a part of 10 plus 2 syllabus. Then 2 mu t cos r is equal to m lambda. It is given for destructive interference. In this case, mu is nothing but refractive index of the medium. T is nothing but thickness of the film. R is angle of reflection, as we are talking about Newton's ring in reflected light. Lambda is nothing but wavelength of the light, and M here provided as the fringe number we can say. So these are the conditions for constructive and destructive interference. Now, as our medium of experiment is air, so we can say, we know for air medium refractive index value is 1. So we need to keep this mu is equal to 1 in the equations provided over here. Then in this case the normal incidence is there. For normal incidence, angle of incidence is nothing but 90 degree. Therefore, angle of reflection, it will be say uh, r is equal to 0, or it is 0. Therefore, cos 0 will be 1. Therefore, if we put these values in equation number 1 and 2, then the conditions will become 2t is equal to 2m plus 1 lambda by 2 for constructive interference, and 2t is equal to m lambda for destructive interference, that we have to use in further calculations. Again we will see the plano-convex lens glass plate system. This is the side view. Now here is the top view. Here you can see the plano-convex lens, and we have taken the top view of the plano-convex lens. Now let's say AB is nothing but diameter and O is the center of the circle or center of the plano-convex lens. CD is one chord that we have plot on the plano-convex lens, and G is the point, which is say a point connecting AB and CD chord. We have taken two normals, one from D to F on the glass plate, and one is nothing but CE on the glass plate. Capital R is nothing but radius of plano-convex lens, and small r is radius of, or it is the distance in between these points B, F. Now we have to consider at point F there is a dark ring or a bright ring. So accordingly, if from here there is a dark ring, say dark ring, then BF will be the radius of that dark ring, and we are going to determine that only. So R that we have seen, R capital R is the radius of curvature of the lens, and a dark ring we have to assume is located at point F. In that case, small r will be the radius of the dark ring. Uh, as this is the plano-convex lens, so df will be the thickness of the air film. So df, and that it will be equal to Ce equal to T. Then if we are considering at point F there is say mth dark ring, then Bf will be equal to Rm. You might have seen a theorem of intersecting chords in mathematics. So according to theorem of intersecting chords, AG multiplied by GB is equal to CG multiplied by GD. That theorem says product of segments of chords on a circle are equal. So for AB, AG and GB are the segments, and for CD, AG and GD are the segments. By putting values of AG, GB, CG and GD, you will get this particular equation. AG is nothing but 2R minus T. GB is nothing but is equal to DF, and we have seen in equation 5 DF is nothing but T. So we have taken T over here. CG, CG and GD are equal to EB and BF. That's why and all are equal. So that is nothing but RM, radius of the M3. So this we have taken as equation number 7. So ultimately we will get R square M is equal to twice R minus T multiplied by T. We have just rearranged this equation. Now in this case, this 2RT is much bigger than T squared. T is nothing but thickness of the film, that is very small, and that's where the T square is neglected in this equation, and that's where if we observe the previous equation, R square M will become 2RT. So from equation number 4 and 9, have a look towards equation 4. So R square M will be equal to M lambda R. For dark ring, this 2R is nothing but M lambda. So that 2T is nothing but M lambda that we have kept over here. So if we take the square root, Rm is equal to under root m lambda r, and that is nothing but the thickness of the radius of the dark ring. So from radius you can calculate the diameter. For different fringes like dark ring number 1, 2, 3, 4, what will be the radius? R1 will be, just we have to keep the values of m is equal to 1, 2, 3, 4 in the previous equation. So radius of first ring will be R1 is equal to under root lambda r. Then R2 will be equal to under root 2 lambda r. R3 will be equal to under root 3 lambda r, and so on. Rn will be equal to under root n lambda r. So from all these equations we can conclude that the radii of dark rings are proportional to the square root of the natural numbers. So these are the natural numbers because lambda r is constant everywhere. So like this, you can determine the radii of bright ring. Just you have For the determination of diameter of bright ring, let's consider at point Q there is a bright ring, and the radius of mth bright ring you will calculate as r square m is equal to 2RT. The same thing you have to follow, that consider the theorem of intersecting chords and then conditions for brightness you have to consider, and at last you will come to the conclusion that radius of mth ring is equal to 2m plus 1 lambda r by 2.
To find out radii of different bright rings, we can substitute m is equal to 0, 1, 2, 3 like this. So for R1, it will be under root 3 lambda r by 2. R2 is equal to under root 5 lambda r by 2. R3 is equal to under root 7 lambda r by 2, and so on. So here we can conclude that radii of bright rings are proportional to the square root of the odd natural numbers.
Now is the time to see where we can apply the knowledge of Newton's ring experiment or interference in our life. So the applications are listed like this. With the help of that you can determine wavelength of any unknown source of light. Then determination of refractive index of liquid is possible with the experiment. We can have the test of optical flatness, then anti-reflecting coating having the principle of the same experiment. Then determination of thickness of wire can be possible through this experiment, and determination of radius of curvature of lens. So we will see all these applications one by one. Let's talk about the determination of wavelength of light. We have seen the radius is nothing but for dark ring, radius is Rm is equal to under root m lambda r. So if we talk about diameter, then diameter will be d square m is equal to 4m lambda r. Diameter is square we have taken. This is for say mth ring. If we consider the m plus p ring, then d square, the equation will become like this: d square m plus p is equal to 4m plus p lambda r. Just replace this m by m plus p. Then by subtracting equation 1 from 2, we can get lambda is equal to d square m plus p minus t square m divided by 4pr. So uh, with the help of this particular formula, we can determine wavelength of any source of light that can be used in Newton's ring experiment. So it is nothing but just square of diameter differences divided by 4 into p is nothing but the distance in between two diameters that we have selected, and r is nothing but radius of curvature of lens. Next application is determination of refractive index of liquid. The same experimental arrangement we have to use for the purpose. Just we have to replace the air medium by the liquid medium. Then we have seen the conditions for interference are given by 2 mu t cos r is equal to m lambda. The in case of normal incidence, we can rewrite this equation as 2 mu t is equal to m lambda. This is the case. Now we have to same consider the radius we will take over here. So r square m is equal to twice rt, that we have already seen. So using equation 2 in equation 1, r square m of liquid is equal to m lambda r by mu. Then if diameter is taken, it will be d square m is equal to 4m lambda r by mu. Here we have written L, means this thing we are talking about Newton's ring pattern in the liquid medium. Now the diameter of m plus p ring, this we have taken for m ring. Now another ring, consider it is m plus p ring, then d square m plus p is equal to 4m plus p bracket close lambda r by mu. So by subtracting this equation, we will get this particular equation. And earlier we have calculated this value 4p lambda r. So 4p lambda r is nothing but d square m plus p minus d square m. In earlier uh, calculations we have seen this. So here the diameter differences of the uh, two rings is equal to diameter differences in the air medium divided by mu. So from this we can calculate refractive index of liquid is equal to square of the diameter differences in the air medium divided by square of the diameter differences in the liquid medium. The third application is checking of optical flatness of any optical material. So for that we have to use the same experiment, just with little modifications. Whatever is the test material, that test material you are going to keep in place of the plano-convex lens. So on glass plate there will be a test material. With this arrangement, if this material is optically flat, then you will get alternate bright and dark lines, as you can see over here. And if there is some kind of error, then there will be an irregular pattern in the view. If in this case the surface is a convex one, then you will get such kind of pattern. For concave, this will be the case. Then anti-reflection coating is one application. Basically, the students who are having lenses, they can understand this particular thing. Generally, while purchasing the specs, we go for some kind of treatment. Coating treatment we generally prefer, because if anti-reflection coating is there, then we can have the clear view that we are interested. Uncoated glass surfaces will give you view like this. So anti-reflecting glare coating or without coating, and with coating you can see the differences in vision. Vision will be clearer in case of coated surfaces. This is due to the fact that thin film interference plays an important role over here. Anti-reflection coating is basically used in various telescopes and cameras where multi-component glass lenses are used. Uh, Basically, if the coating is not there, then what will happen? As we have seen, in case of a thin film, if on a reflecting surface, if a light ray incident, then most of the portion get reflected. So in order to have avoid the reflection, much amount of reflection, we need to have the coating. So that kind of coating was first made by Alexander Smakula, who was working with Carl Zeiss company. He has introduced a transparent film of dielectric material on the lenses, and that thin transparent film coated on a surface in order to suppress the reflection is called as anti-reflection coating. So this is all about the anti-reflection coating and the applications of Newton's ring experiment, or we can say interference in a large amount. So this is all about Newton's ring experiment. For any kinds of doubt, we will have further discussion. Thank you very much.